There is a peculiar kind of darkness at the edge of the solar system. Not the dramatic darkness of science fiction, no crackling void, no foreboding silence, just distance, enormous, indifferent distance. The kind that reduces the sun to something smaller than a thumbnail held at arm's length. The kind that takes light, which travels at 300,000 kilometers per second, over 4 hours to cross. At that distance, there is a planet. It is roughly 4 times the diameter of Earth. Its atmosphere moves faster than the speed of sound. Its interior may be raining diamonds. And for most of human history, no one knew it was there. This is Neptune, the 8th planet, the last one. The calculation that found a world. Every planet in the solar system was found the same way. Someone looked up, noticed a wandering light in the sky, and followed it. Mercury, Venus, Mars, Jupiter, Saturn, all discovered by eye, across cultures, across centuries. Uranus, found in 1781, was the first planet discovered with a telescope. But even then, the method was the same. You pointed an instrument at the sky, and the planet revealed itself. Neptune was different. Neptune was not seen first, it was calculated. In the early 1840s, a French mathematician named Urbain Jean-Joseph Le Verrier was studying the orbit of Uranus with unusual care. Uranus had been tracked for decades by then, and something was wrong with its path. It was not moving the way Newtonian gravity said it should. The discrepancy was small, barely perceptible, but it was consistent, and consistency in anomaly is the beginning of discovery. Le Verrier formed a hypothesis. The only explanation that accounted for Uranus's irregular motion, he reasoned, was that another planet existed beyond it, one massive enough and close enough to be pulling on Uranus in ways that hadn't been accounted for. He did not go looking for it with a telescope. He sat down and computed where it had to be. In 1846, he sent his prediction to Johann Gottfried Galle at the Berlin Observatory. Galle turned his telescope to the precise coordinates Le Verrier had specified. Within a single hour, he found the planet. It was almost exactly where the mathematics said it would be. This was not luck. This was one of the most precise demonstrations in the history of science that the universe obeys rules, and that those rules, correctly understood, can reveal things no eye has yet seen. Neptune was the first world that human reasoning discovered before human vision confirmed it. A place beyond reach. Knowing Neptune exists and knowing Neptune are different things. It orbits at roughly 30 astronomical units from the Sun, approximately 4.5 billion kilometers. To put that in terms of travel time, using the fastest spacecraft technology currently available, it takes about 13 years to get there. In Neptune's sky, the Sun is 1/30th of the size it appears from Earth and delivers roughly 1,000th of the light. The planet receives so little solar illumination that it can barely be resolved through most ground-based telescopes even now. The orbit itself is almost incomprehensibly slow. A single Neptunian year, one complete circuit of the Sun, takes 165 Earth years. We discovered Neptune in 1846. We have watched it complete exactly one full orbit since then. 1 year in Neptune's experience spans the entire modern era of science. And at certain points of its path, Neptune drifts further from the Sun than Pluto. Beyond it, there is very little. Icy rocks, the Kuiper Belt, then the long, dark crossing of interstellar space. Studying Neptune from Earth was always going to be difficult. The only real alternative was to go there. And going there required not just engineering, but timing.
Voyager's Grand Tour. Once every 175 years, the outer planets align in a configuration that allows a spacecraft to use each one's gravity as a slingshot to the next, a multi-planet trajectory that no fuel budget alone could achieve. NASA recognized this alignment was approaching in the 1970s and built a mission around it. Voyager 2 launched in 1977. Over the next decade, it swung past Jupiter, Saturn, and Uranus, each flyby accelerating it toward the next target. On January 25, 1986, it departed Uranus and turned toward Neptune, the final destination, the last planet on the tour. It traveled at 54,000 kilometers per hour. It took 3 years. On August 25, 1989, Voyager 2 passed within 5,000 kilometers of Neptune's North Pole, the closest approach in its entire mission. In a matter of hours, it sent back more information about Neptune than all the decades of ground-based observation combined. What it revealed was not what anyone had expected.
What the storms tell us. Neptune should, by most conventional reasoning, be a quiet place. It receives almost no solar energy. Heat drives weather on Earth, on Jupiter, on Saturn. At 4.5 billion kilometers from the Sun, there shouldn't be much weather to speak of. But Neptune's atmosphere moves faster than the speed of sound. Voyager 2 measured equatorial wind speeds approaching 2,160 kilometers per hour. Most of those winds blow in the opposite direction to the planet's rotation, retrograde flow, working against the spin of the world beneath them. The reasons are not fully understood. And riding those winds at the time of the flyby was a storm roughly the size of Earth. It was called the Great Dark Spot. It rotated counterclockwise, like a cold atmosphere mirror of Jupiter's Great Red Spot. Its internal winds reached 2,400 kilometers per hour, the fastest ever recorded in the solar system. When Hubble turned toward Neptune in 1994 to check on it, the Great Dark Spot was gone. This is the part that is quietly striking. Jupiter's Great Red Spot has persisted for at least 3.5 centuries. Neptune's equivalent formed, raged across a planet the size of Earth, and dissipated all within years. Storms here are not features, they are events. They arise and vanish on timescales that are, by planetary standards, almost rapid. Other storms have appeared since. A significant vortex was observed in 2015. It too faded. The Hubble Space Telescope is, at present, the only instrument capable of monitoring these changes reliably, because in most light wavelengths, Neptune's storms are nearly invisible. Hubble's ultraviolet capability changes that. It can probe the atmospheric bands in ways that make the weather legible. The deeper question is why the weather is so extreme to begin with. Neptune receives 1,000 times less solar radiation than Earth. Its storms should be feeble by comparison. Something else is providing the energy. That something is heat, but not the sun's heat. Heat from below. Neptune is not the coldest planet in the solar system. That distinction belongs to Uranus, which is smaller, closer to the Sun, and almost eerily still. The reason Neptune is warmer than Uranus, and the reason its weather is so much more violent, appears to come from within. Neptune radiates significantly more heat than it receives, nearly twice as much energy out as in. This excess is almost certainly primordial, heat left over from the planet's formation, slowly bleeding outward through convection in the deep interior. Uranus, by contrast, radiates almost no internal heat. Current thinking holds that a large impact, possibly an Earth-sized body, struck Uranus billions of years ago and disrupted the convective processes that would have transported heat from its core. Uranus retained the heat, but locked it away, unable to release it. Neptune was spared that disruption. Its interior is still warm. Its atmosphere knows it. This internal heat drives the convection that powers Neptune's storms, sustains its winds, and generates the dynamic, turbulent weather patterns that should, by the logic of solar distance alone, have no right to exist. The interior and what might fall there. Below Neptune's atmosphere, below the hydrogen and methane gases that give the planet its deep blue color, lies something more difficult to characterize. The prevailing model describes a layered interior, a rocky, iron-rich core surrounded by a liquid mantle composed of water, ammonia, and methane ices under extreme compression. At the boundary of these layers, the pressures reach approximately 7 million times the atmospheric pressure at Earth's surface. Under those conditions, something unusual may be happening to the carbon. At sufficient pressure, carbon atoms can be stripped from methane molecules and reorganized into something denser. Laboratory experiments using laser-driven compression to briefly replicate Neptunian interior pressures have suggested that the result could be diamond, not in any form we would recognize, but as a liquid or as solid crystals falling through a carbon ocean like hail through storm clouds. Diamond rain. It remains a hypothesis. The experiments that support it are recent and still under scrutiny, but the pressure calculations are sound, and the physics, at least in principle, permits it. Neptune may be, in its deepest interior, a world of falling diamonds. Rings, offset magnetism, and faint light. Neptune has rings. This was confirmed by Voyager 2, though they are among the least conspicuous in the solar system, dark, diffuse, difficult to see against the black backdrop of deep space. There are 5 known rings, each named for a figure connected to Neptune's discovery or study. The innermost, Gale, is wide and faint. Le Verrier is narrow and brighter. Lassel and Arago are faint bands. The outermost, Adams, is the most studied and the strangest. Within the Adams ring are structures called arcs, regions where the ring material clusters more densely rather than distributing evenly around the orbit. Arcs imply confinement. Something is gathering the material and preventing it from spreading. The mechanism responsible remains unknown. The arcs have persisted since they were first identified in 1980. Whatever is holding them together has been holding them for at least 4 decades. Neptune's magnetic field carries its own peculiarity. It is offset from the planet's rotational axis by 47 degrees, sharply tilted in a way that Earth's magnetic field is not. When Voyager 2 found the same anomaly at Uranus, astronomers initially attributed it to Uranus's extreme axial tilt, but Neptune's axial tilt is unremarkable, close to Earth's. The shared magnetic offset suggests a shared cause, most likely related to the electrically conducting liquid mantle, which may generate or distort the magnetic field independently of the core. This tilted magnetosphere also shapes Neptune's aurorae. They are faint, far fainter than Earth's, and they appear not at the poles where aurorae typically concentrate, but at the mid-latitudes. For decades, they were effectively invisible. In March 2025, the James Webb Space Telescope changed that. Using its near-infrared instruments, Webb captured images of Neptune's mid-latitude aurorae, shimmering bands of light stretched across the planet's atmosphere, the first clear images of this phenomenon. Webb also detected something unexpected in the same observation, a dramatic cooling of Neptune's upper atmosphere. Temperatures had dropped by hundreds of degrees since Voyager's measurements in 1989, nearly halving in the intervening 3.5 decades. What is causing this cooling and what it means for Neptune's atmospheric chemistry and storm dynamics is not yet understood. The observation has opened more questions than it has closed. Triton. Of all the things Voyager 2 discovered at Neptune, Triton is the most remarkable. It is the largest of Neptune's 14 known moons, comprising 99.5% of all mass orbiting the planet. It is larger than Pluto. It has an atmosphere, thin, barely there, but present, a nitrogen shell roughly equivalent to Earth's atmosphere at 80 kilometers altitude. It has weather, it has seasons, and it has volcanoes. But Triton does not belong here. Every large moon in the solar system orbits in the same direction as its parent planet's rotation. This is the expected outcome of formation. Moons coalesce from the same disk of material that forms the planet, and so they spin with it. Triton orbits clockwise, while Neptune rotates counterclockwise. Its orbital plane is inclined 130 degrees to Neptune's ecliptic. It is, by every indication, a captured object, a dwarf planet that once roamed the outer solar system and was caught. The most plausible scenario involves a binary system. Triton may once have been paired with another Kuiper Belt object, a companion, orbiting it, in the way Pluto is paired with Charon today. As this binary pair crossed close to Neptune, Neptune's gravity disrupted the system. Triton's companion was flung away. Triton, in losing that companion, also lost enough orbital energy to be captured. Its similarity to Pluto goes beyond this hypothetical origin. When New Horizons flew past Pluto in 2015, the surface compositions matched closely: nitrogen ice, traces of water and carbon dioxide, reddish patches of organic compounds called tholins formed when methane is irradiated by ultraviolet light. They appear to be siblings, both born in the same region of the outer solar system, separated by an encounter with a planet. What makes Triton geologically active is its captured status. The gravitational strain of orbiting Neptune in a retrograde direction creates tidal stresses within the Moon, and those stresses, combined with radioactive decay in its rocky core, appear to be sufficient to maintain a subsurface ocean of liquid water. The evidence for this ocean is indirect but consistent: a surface that is geologically young, constantly renewed, caldera-like depressions that are the signatures of cryovolcanism, vast plains of solidified liquid water, what geologists call planitia, bounding by walls like frozen lava lakes. Voyager 2 photographed plumes erupting from Triton's surface, reaching 8 kilometers high. These particular eruptions may be driven by a greenhouse mechanism, sunlight penetrating the transparent nitrogen ice, warming darker organic deposits beneath, sublimating a pocket of gas until the pressure breaches the surface. But the cryovolcanic processes that renew the larger terrain appear to be driven from deeper within. If there is a subsurface ocean, and if that ocean contains the organic compounds that Triton's surface abundantly displays, then Triton joins a small list of worlds in the solar system where the conditions for life, not life itself, but the prerequisite chemistry, appear to exist. It is a list that includes Europa, Enceladus, and Titan. Triton is being pulled slowly inward by tidal forces. In roughly 3.6 billion years, it will cross the Roche limit and be torn apart, scattering its material into a ring system that will briefly rival Saturn's before dispersing. The Moon exists on a long countdown. The outer system. Beyond Triton, Neptune has 6 more irregular moons, likely captured objects with eccentric orbits that take years to complete a single circuit. Their irregular paths were probably shaped by interactions with Triton during or after its capture. The outermost 2, Pasamaphie and Neso, hold the distinction of being the most distant moons of any planet in the solar system, taking roughly 25 years to complete a single orbit. Neptune can hold them that far out because its hill sphere, the region where its gravity dominates over the Sun's, is unusually large. This is a consequence of distance. The further a planet is from the Sun, the weaker the Sun's gravitational competition, and the wider the zone the planet can claim as its own. In 2013, Hubble discovered a new moon, now named Hippocamp. It is small, roughly 35 kilometers across, and orbits in close proximity to the much larger moon, Proteus. Proteus bears the scars of a violent impact history, its surface marked by craters 50 to 100 kilometers in diameter. The most likely explanation for Hippocamp is that it is a fragment, material ejected by one of those impacts, pulled into orbit by Neptune's gravity, persisting there ever since. One additional object merits attention. The trans-Neptunian body, designated 2020 VN40, orbits the Sun in a precise 10-to-1 resonance with Neptune. For every 10 orbits Neptune completes, 2020 VN40 completes 1. Its orbital period is approximately 1,650 years. It is highly inclined relative to the ecliptic. It is not a moon. It orbits the Sun, not Neptune, but it is gravitationally choreographed, held in a delicate mathematical relationship with the planet. It is a small demonstration of how far Neptune's gravitational influence reaches and how it quietly shapes the outer solar system, even for objects it does not technically own.
What we don't know. It is worth sitting with how much remains unknown. We have visited Neptune exactly once. Voyager 2's flyby lasted hours. The images it returned, the measurements it made, those are still the primary source of direct data we have about the planet. Everything else is inference. Hubble's ultraviolet observations, ground-based spectroscopy, and now Webb's infrared capability. The cause of Neptune's extreme wind speeds is not fully explained. The mechanism sustaining the ring arcs has not been identified. The source of the atmospheric cooling Webb detected in 2025 is under investigation. The internal structure of the planet remains modeled rather than measured. The subsurface ocean of Triton is inferred, not confirmed. There are no confirmed missions to return to Neptune. NASA, facing significant budget constraints, has no Neptune probe in active development. China has proposed a mission that could launch as early as 2033. Whether it proceeds depends on factors that have nothing to do with science. In the meantime, Neptune continues its slow circuit of the Sun, one orbit every 165 years, currently in its second year since discovery. The southern hemisphere in spring, warming slightly, brightening faintly, releasing methane into the stratosphere. Changes that, against the scale of the planet, are barely perceptible, but real.
There is something fitting about Neptune being the hardest planet to reach. It was found by logic before it was found by light. It was visited once by a spacecraft that used a 175-year planetary alignment and 12 years of travel time to get there. Its largest moon is a captured world from another part of the solar system. Its storms form and dissolve faster than Jupiter's have changed in centuries. Its interior may rain diamonds. Its aurora was invisible until a telescope powerful enough to see it finally launched. Every fact about Neptune required something extra. Extra mathematics, extra time, extra technology, extra patience. That seems appropriate for a place this far out. Neptune is not the most dramatic planet in the solar system. It does not have Saturn's rings or Jupiter's scale, but it is arguably the most instructive. A reminder that the solar system does not give up its most distant secrets easily, and that the rewards of persistence have a way of exceeding the effort spent. The final planet, still largely unknown, still waiting.